Hello and welcome to the presentation for the paper Context Preserve and Data Augmentation for Sequential Recommendation. I'm your presenter, Benjamin Amankwata. This paper was co-authored by myself and Dr. Kenneth Fletcher, who's my advisor and the director of the Computing Services Lab here at UMass Boston. We begin with an outline of this talk. We will discuss our motivations, followed by the contributions, and then we'll delve into the details of our model. We will present our research questions as well as our experiments and results, and then we'll conclude and present directions to extend this work in the future. So our motivation. It is well understood that item ordering in user historical interaction encodes important item relation signals that are crucial for sequential recommendation. We also know that most of the user historical interaction training data for sequential recommendation is induced by an underlying candidate generation process. For example, if you use an online service such as Netflix or Amazon, then the order in which items are presented to you is not endogenous. It is usually the result of an underlying recommendation system or some other ranking mechanism. We argue in this paper that rigidly adopting the item ordering that the underlying candidate generation process provides distorts fundamental item relation signals that are crucial for item representation learning and ultimately leads to suboptimal sequential recommendation. As a result, we present the following contributions. We propose an effective self-supervised approach for recovering and amplifying item relation signals for superior item representation learning. We propose an efficient algorithm to create and sample diverse user historical interaction sequences for data augmentation that preserves both local and global contextual information. We propose an approach for next item presentation recommendation that significantly outperforms the majority of the state-of-the-art baselines on 7 public datasets. We begin with a brief overview of our model. So our model has 3 main components. The first component is the data augmentation component, which employs strongly restricted permutations, which is represented at the bottom left corner of your screen. The second component of our model is an N-layer Roberto encoder, and this encoder produces a contextual item representations. And then finally, we have a sequential recommendation based on convolutional neural networks that takes as input a representation generated by the bi-directional encoder, and then produces a compact representation, which is fed to a feed-forward network, a multi-layer perceptron with softmax to generate a rank list of next items for recommendation. So we'll discuss the first component of our model, which is the data augmentation with strongly restricted permutation. And here, our objective is to amplify item co-occurrence and interactional context signals without distorting both subsequence level and full sequence level context, which are local and global context. And our approach is to augment user historical information interaction from the training data set by sampling from strongly restricted permutations that are generated from the training data. We consider permutations where each item in the user historical interaction can be displaced up to k positions to the left or right of its original position. And this approach is inspired by, longstanding work in distributional hypothesis in natural language processing, as well as our own recent work in interactional context. We will go over in detail our algorithm for data augmentation, which is a modified version of a random transposition walk. Algorithm takes as input a sequence S representing the user historical interaction, a displacement D representing how many positions an item is allowed to move to the left or right of its original position, and then P, which is the number of permutations to return, and C, which is the number of candidate permutations to generate. And we will touch more on why this is necessary. So the first part of the algorithm involves creating an interval restriction matrix. And an interval restriction matrix essentially encodes the positions that items in the sequence are allowed to be displaced to. So it's a square matrix whose elements can be either 0 or 1. And it has the property that if aij is 1, then an element at position I in the input sequence S can be displaced to position J in the input sequence. And so we construct the interval restriction matrix as follows. We loop over all the positions, and then we ensure that if a position's displacement is within the displacement interval, that we set that position to 1. Um, Whereas the matrix itself is initialized to all zeros, and then we set it to 1 if the position is within the allowed interval displacement. Next, we begin to generate the permutations. We initialize a set of empty sets to collect the permutations that I generated, both the final one and then the candidate ones. And then we initialize a current permutation C to the input sequence. Next, we sample 2 positions from the input sequence. And we sample 2 positions, from the current permutation. And then those 2 positions, I1 and I2, using I1 and I2, we reference the values, that is the actual items at I1 and I2 in the current permutation. And then we look up the positions of those values in the original input sequence and obtain those positions I and J. Then, using the interval restriction matrix, we verify that both aij and aji are both allowable according to the interval restriction matrix. And if they are, then we swap positions I1 and I2 in the current permutation to create a new permutation, and then we add that permutation to the list of candidates. And we continue with this process until we've generated the required number of candidates. Then from the set of candidate permutations, we sample the actual number of permutations that we need to generate. Now, this is important because our algorithm is a modified random transposition walk, and so every subsequent permutation um, differs from the permutation from which it was generated by one swap. And so to create diversity in our sampling, we actually have C much greater than P, so that we can generate a diverse pool of candidate permutations from which we can sample the prerequisite number of permutations that we need to return to have diversity in the samples. Next, we'll talk about item representation learning. And here, our objective is to deepen the contextualized embeddings extracted from the transformer-based encoder. And our approach here is as follows. So given a sequence of n tokens representing the UHI, T1 through Tn, and a k-layer transformer encoder, which outputs a representation, an n by d representation at each layer, where n is the sequence length and d is the embedding dimension of the transformer. We obtain a final representation that is 3 by n by d of the sequence by stacking the outputs of the final 3 layers of the encoder, where d is the embedding dimension of each encoder layer. And so graphically, we take n tokens and run it through k layers of a Roberta encoder, and then we take the representations of layer k minus 2, k minus 1, and k, and we stack them together, and we have our input sequence representation. And the final component of the model, obviously, is the convolutional neural network for sequential recommendation. The input to the convolutional neural network is the representation 3 by n by d obtained from the transformer encoder, as we mentioned. And the output of the CNN is a compact vector of size 128. We will present a detailed description of a CNN architecture in the next slide. So a CNN architecture, as we mentioned, takes the input sequence representation that we have described, and it treats each layer output of the transformer of the 3 layers as a separate channel to the CNN. And then we have a number of CNN blocks that comprise, the convolutional layer, a ReLU layer, and a pooling layer, and then some regularization. And then it generates compact vector representation, which we pass through a multi-layer perceptron and a softmax to predict the next item. Okay, so now we'll talk about the experiments that we run, and briefly we'll talk about the data sets that we used. We used Yelp, the Yelp data set, which is a subset of Yelp's business reviews and user data across 8 metropolitan areas in the US and Canada. Foursquare, the global check-in data from Foursquare. It contains check-ins for users in cities across 77 countries. And we also used the Movie Lens 25 million database, which user movie interaction activity from a movie recommender service. Last FM1K, which is the whole listening habits for nearly 1,000 users. AOTM, out of the mixed platform data on listening behavior of users. 30M music, and now playing music listening behaviors of users created from mining from social networks. And we have some metadata for the data sets here. Movie Lens has 130,000 users, close to 8,000 items, and close to 9 million interactions. Foursquare has 227,000 users, 14,000 items, over 7 million interactions. Yelp has close to 500,000 users and a little over 7,000 items and close to 3 million interactions. Last.fm has 414,000, almost 415,000 users and 13,000 items, 13,400 items, and a little over 5 million interactions. And then similar information for 30M, now I'm playing, and OATM. So our research questions were as follows. The first is, how does our convert model perform on sequential recommendation compared to the existing state-of-the-art models? And the second research question was, what is the contribution of our proposed strongly restricted permutation data augmentation approach to the overall performance of our model? And then the third research question is that, can existing state-of-the-art models for sequential recommendation benefit from our proposed data augmentation approach? And we will answer these questions with the results from our experiments. So for research question number one, how does our model compare to the state-of-the-art sequential recommendation models? We observed that our model outperforms existing baselines on all the 7 data sets that we compared with, and that the average performance improvement across all the baselines is about 94% for MRR and 80% for recall. On this table here, we present the performance comparison again between our model and the state-of-the-art sequential recommender models, and we also present the improvements in performance of the other models when we add our data augmentation approach. So we can observe from this table that on average we notice an improvement if we apply our data augmentation approach to the data before it is fed to all of the state-of-the-art models. So it seems to make a huge difference if we apply the data augmentation to the training data set before we feed it to any of these models which were not designed with our approach in mind. So the average baseline improvements for MRR across all the different data sets when we apply our SRP model is close to 14% for GRU for rec, minimal for Kaiser, over 50% for bed for rec, and again over 50% for SAS rec. And for recall as well, we have over 10% for GI for rec, 2.25 for Kaiser, and almost 45% for bed for rec, and over 55% for SAS rec, which we think is significant. So in conclusion, in this work, we propose a two-stage technique to recover and amplify item relation signals, which are compromised in the training data for sequential recommendation. We recover compromised signals with a novel data augmentation process that involves generating synthetic user historical interactions from observed UHI samples. In the second stage, we employ a self-supervised pre-training approach that leverages the recovered item relation signals to learn superior item representations. We develop a novel CNN-based sequential recommender model as a downstream task to utilize our learned item representations. We demonstrate that our approach is able to recover item relational dynamics distorted by the candidate generation process. Our proposed model also significantly outperforms our four state-of-the-art models for sequential recommendation, and ablation study confirms that our item representation and approach is a significant contributor to the model's superior performance. We find that the vast majority of our compared state-of-the-art baselines also enjoy a significant performance boost from utilizing our learned item representations. In the future, we would like to extend this work to explore the properties of item relation signals that are recovered or recoverable, and to explore neural approaches to optimize item signal recovery. And with that, we've come to the end of this presentation. We thank you for your time.